Now, I've given this talk in a number of places, and this includes talking to people in my field. By the way, I'm a condensed matter physicist, theoretical physics, but I do my research from purely theoretical physics in condensed matter physics. And I've given this talk both to pure physicists and also to a larger community of scientists and engineers. And this include, I think, 2012 PyCon US at Silicon Valley. And the first thing here, when I came here, is I know we are going to have a number of developers, but I don't know if we will have teachers in colleges and universities here. Are there teachers? Okay, just two. Yeah, it's the usual thing. Okay. It is also very good. I'm not disappointed because this talk is not directed to the teachers alone, but it's also directed to the developers. My reason is very simple. Over the years, we've moved this project from just looking at physics principles, laws, or experiments. We've done something on illustrative website. And when I was doing this illustrative website, I put some of my students as projects, and we needed a developer to teach them the jungle and how to design a website. So this is why this kind of talk is also good for developers. And my encouragement also comes from, I think, 2013 PyCon in the US, or maybe in the one in Canada this year. It was, no, sorry, last year. There was this female who, did a serious research work in the US to know how people are using computers in the colleges. And she got so disappointed, and she made a presentation at that PyCon meeting. And he said that we are talking about how to bring in the computer to the world. But where we have to start from, we are not even starting from there, and that is the colleges. So here in a community like this, the developers are here talking about how to move the Python community to increase the community. But how much are you doing by even visiting your local college or university to know what kind of software they are using there? Maybe you will be surprised that in some of these places, they are using assembly language. Don't be surprised. They are using assembly language. And meanwhile, you are a developer in the same time, you are using Python and maybe some other sophisticated languages. And you see, the teacher may not have the confidence to come to you to say, hey, I want to learn this thing. Many teachers will not do it. It's only a few people like me, because my philosophy is that for the fact that I am a teacher, I'm a student all my life. That is my philosophy. I keep learning. And whoever, even if it's a kindergarten, if I can learn something from you, I will come to you. That is my philosophy. But many teachers will not do it. So you'll be in a town, developing wonderful projects with Python, but the student in your place are learning assembly language. So I think I have encouraged somebody today, by the time you get back, visit the university, visit the college that is close to you, and know what kind of language they are using, and see how you can come in. Thank you. All right. So I have also tried to reduce my presentation, because I won't want to bore you people with equations. When you present to a gathering of scientists and engineers, then you know what to do. But when you present to developers, you avoid a lot of equations. So the plan, as you can see, we just say, why computational approaches? Then we look at the choice of a program, Python, Africa Computational Science and Engineering Project. Then we look at set packs, which are some of the examples we have developed over the years. We also look at the problems and prospects of the pack set in other Africa countries. Okay, why computational physics? If you look at the picture there, that is Rutherford. Rutherford is acclaimed to have discovered the nucleus. Of course, the atom is made up of basically the electron revolving around the nucleus, and the nucleus, which contains the proton and the neutron, was actually discovered by Rutherford. If you see the experimental setup there, that is all the equipment that Rutherford and his assistants needed. So we have to think of it this way. As at then, if you invite Rutherford to come and perform his experiment, he could have taken everything there into a bag, carried it, get a train, and come to you wherever you are to demonstrate how you can see that the nucleus is actually at the center of the atom. He could have done that by carrying the whole of his lab in a bag. That is what we know. Then let's look at this. I don't know how many of us have heard of the Higgs particle, which is known as God's own particle. And they discovered it at the Large Hadron Collider. It was said it has been discovered, though many scientists are saying it has not been discovered. Okay, we won't go into the nitty-gritty of that. But the point is that what you are seeing here is a setup just to discover the Higgs particle. And if you compare to look at just a lab to discover the nucleus, but now look at another lab, the facility, to discover the Higgs particle. This one has 10,000 scientists and engineers from over 100 countries with billions of naira at the Large Hadron Collider, and is the largest and most powerful particle accelerator with a 27 kilometers ring of superconducting magnet, mainly to do what? To prove or disprove the Higgs particle. This is to say that science has moved from when the scientists can carry the whole experimental facility in a bag to a situation where the facilities now occupy a whole town. That is it. Okay, that is on the experimental side. Let's look at the theoretical side again. Why are we doing computational physics? That is Isaac Newton. A poet said that there was darkness in the light in the world, and God said, "Let Newton be," and there was light. The truth of the matter is that Newton gave us all the laws that seems to govern the classical world. So, and we were told that he could just sit under an apple tree, maybe one apple falling upon his head, and he begin to imagine how it happened, and from there, begin to write equations, and at the end of the day, you have the Newton's laws of motion. Okay? That is the theoretical side. But today, let's look at the other side. This is the phase diagram of superconductivity. By the way, this is where I'm doing my research. And if you look at the phase diagram, you see several phases. You see the insulator at the ferromagnetic phase, the pseudo gap, the strange matters. Imagine, they couldn't do anything, so they just have to call that phase strange matter because they know nothing about it. Then you have the Fermi liquid. I can tell you, superconductivity was discovered more than 100 years ago. Then in 1956, Bardeen, Cooper, and Skripia, they came up with a theory known as the BCS theory, which could account for superconductivity. But it was discovered it could only account for metals and alloy. In 1986, they discovered a new set of superconductor with relatively high temperature, and that is the superconducting cuprate. Since then, there is no new theory. I can tell you some of the best brains, those you know, which include Albert Einstein, Dirac, even Fermi, they have all worked on superconductivity, but there is no new theory up to today. And I can also equally inform you that pseudo gap, which of course is the precursor to the superconducting state where you have the TC, every week you see hundreds of papers from the intellectual community, everybody suggesting all kinds of things, yet there is no theory yet. And all this have moved from when Newton could sit under an apple tree to a situation where you have to use the computing power. The kind of work people do today, theoretically, you can't solve analytically. You just need the computing power. So, ladies and gentlemen, for this reason that both the experiments have moved from small bag to a town facilities, and the theoretical part has moved from just sitting under an apple tree to billions of papers and billions of computing hours, so we need computational physics. Okay, today, it's no longer news that computer and computer-based activities have pervaded our teaching learning process as well as research, so much so that in addition to theory, before now we have what we call the traditional theory and experiment. You do the theory in the classroom, then you test it in the experiment in the lab. But today we now have what a third leg, which is what computational physics. As a matter of fact, I quickly inform you that it's no longer in use that the 21st century scientist and engineer cannot function effectively without some level of computational science and engineering. Okay, so for the teaching learning process, what are we doing? We just see computational physics as a means of understanding the various disciplines in science and engineering, that is at the college and undergraduate level. We also see it as a way of training for the future in academic, industry, and etc. I have it on record that my students, for example, I teach them physics, but when they graduate, they can work virtually anywhere because of their level of computational physics. They can work in the banking industry. They can work in the oil company. Just name it, because we have actually given them the necessary computational background to fit in anywhere. Okay, so while doing this, you need to retain the qualities that are characteristics of such discipline. If it is physics, if it is mechanical engineering, electrical engineering, of course, they are core courses which every undergraduate must know. And these courses, they are so compact. But we need to introduce computational physics. And in doing so, we have to really sit and discuss the philosophy of what computational physics means and how we can incorporate it into the already crowded courses. Then we also do it in such a way that the students should have ability for integrated understanding and adaptive learning. Now, for research purpose, it provides a testing ground. Of course, there are certain stories like the one I showed you, superconductivity. You cannot really do it. The theorists can only, or the experimentalists can only do a little bit. And with the limit of facilities, they can't go on. So what do? You lay the power of computer to predict beyond what both the theorists and the experimentalists can do. They will also see it as a useful tool for analysis, interpretation, and experimental results, and a powerful technique for simulation, that is to predict properties of systems, models that are not easily accessible to experiments. In fact, most of the weather focus you talk about today, they are usually from where? Computational physics and engineering. Okay. Now, when we talk of choice of programming, making a choice depends on the individual, maybe the university or the laboratory, okay? And, but however, there are two basic things we consider when making a choice here. And the first is the desire to ease the learner into programming and to give them the opportunity to develop a conceptual model of what a program is and what it does. Then, more importantly, its accessibility, especially in developing countries or what you call low-income earners. This is very important, and this is why one of the reasons we have adopted Python. As you all know, it's an open and free software. So, if you are in the creek, you are in a river area, wherever you are, all you need, have access to the internet, then what you can do, you can download the whole stuff, including all the necessary model you want to use, and immediately begin to do what? Use it. And this is very good for African countries. I don't know South Africa. Okay, choice of programming language. The choice is Python. Adam just gave us all the good, the bad, and the ugly of the Python programming language. So I'm not going to emphasize on that, but you know, easy to read code. Then he said easy to teach and I want to add to his list, easy to learn. Python is very easy to learn. So I'm not going to give you much, but what I want you to know is that it has several modules, such as NumPy, SciPy, SymPy, Matplotlib, and VPython, which simplifies scientific computation, visualization, and simulation. This is why we have adopted Python. Then further, it is easy to combine if you want to increase the speed or whatever with C, as we have heard. People are still working on CPython, people are working on JPython and the rest of them, Jython and the rest of them. Then what we often tell our students, just to encourage them, is that, see, this Python we want to teach you, it's a very powerful language, that a good percentage of Google is programming Python. So as I'm teaching you, know that you have market value. And the students are really encouraged that you can see it in your local phones, you can see your iPads and the rest of them. So that is the choice of the programming language. Now, the aim is to, what is the Python Africa Computational Science and Engineering Top project? Well, its aim is to introduce computational approach in science and engineering to Africans in Africa via teaching Python to students, new beginners, as well as expert programmers. We use Python to model, simulate, and visualize concepts, laws, and phenomena in science and engineering to complement the teaching of theory and an experiment. As I said, computational physics is now what? The third leg of science, or third pillar of science and engineering. Then we use Python to model, simulate, and visualize laboratory experiments. We are going to see this very soon. So let me not emphasize. And some of the products we already have, we call them pack set packs. So we see one or two examples of this. Now, it was launched in Nigeria on that year, 2010 at ISOPAN 2010. Of course, it's a forum for theoretical physicists. It's an international seminar on theoretical physics and national development. So since then, we've been having it as a postgraduate program at the National Mathematical Center, Abuja. And we do get participants from many African countries. The National Mathematical Center is actually a government-owned center which is built or rather to replicate the International Center for Theoretical Physics that is based in Italy. So what we are saying, instead of going to Italy, why not come to Nigeria and do your research? So this is where we're organizing the foundation postgraduate course. Then participants are usually taught as an introduction, numerical calculation. And that is one of the beauty when we introduce all these people to Python. We say, okay, you can use it even as a calculator. 2 plus 2 gives you 4. They say, yes, this is cool. Sin 30 gives you an answer. Irradiance, then you convert to degrees. This is cool. So you can use it for numerical calculation. You can also use it for symbolic calculation. Then the graphical analysis using Matplotlib is wonderful. You know, of course, Matplotlib was developed by those who were, those who have very elegant knowledge of MATLAB. As you can see the name. I think Matplotlib is almost exactly like MATLAB. The difference is that one is free and one is not free. That is just the difference. And you know, MATLAB has some of the best graphic features you can think of. And this is what we have imported into Python. So we also use it to implement generalized algorithm in science and engineering. Then we introduce them to my project, which includes to model, simulate, visualize laboratory experiments, and to aid the teaching and learning of this. So, okay, I want to quickly talk about the pack set. As I said, I won't bore you with difficult programs, but one of the simplest experiments, I think the teachers here, they know, in college, is the simple pendulum. The simple pendulum, that is the simplest experiment. And what we have done here is to simulate it. So what you see there is actually the simple pendulum experiment as you will have it in the lab. So you have the string, you have the bulb, and attached to a wall. And this is one of the beauty of Python, where we teach it to people, and maybe that is what I will encourage the developer to do. VPython is a very powerful tool and ready to engage young people, because you see sphere, you put a circle, you press enter after you have imported VPython already in the VPython environment. Then you see a round ball coming white. Then you can just add color. That is the code. With a line of code, you say sphere in bracket, parentheses in bracket, you enter. Then you see a sphere, a ball coming out. Then you can color it whatever way you want. You can create a wall on the left or on the right. You create a ceiling, and these are very simple codes. Then you create a floor. Then with a simple Newton's equation, you can ask that ball to move to that around that wall, and students will be seeing it. You can create even a projectile motion, where, of course, in a projectile, it depends on the force. If you increase the force, then the ball will fall further from the wall. You can create that easily. And when you are doing these things, students will just be saying, wow. And the beauty of it is that the codes are using are not complicated, few lines of code. And this is very captivating for students. So in this case now, you have the simple pendulum. This simple pendulum, as we know from college physics, does not depend on the size of the ball. If you like, increase the ball size or the mass to whatever level, it doesn't change the periodic time. What changes the periodic time is the length. So where we have this, we ask students, as you can see from the formula there, that is, the periodic time depends on the length, that the square root of the length. Yg is the acceleration due to gravity. So now it varies with length, it varies with the rate of oscillation, varies. What we did now is that we vary the length, and students will see the oscillation, and they record it from different lengths. In this case, we started with 10 meters, they ended up with 2 meters. Then we recorded the periodic time. Then also, you can vary the size of the ball, but you discover that when you vary the size of the ball, it doesn't affect the periodic time. You increase the rate of oscillation, it doesn't affect it. You change the number of oscillation, it doesn't affect it. And this is what we expect our students to understand when they go to the physics lab. And when they go there, if they can do it without clumsiness, this is what they will see. And here they will be watching it like a video and see it live. And after they have done that, then they have the length, they have the periodic time. And with matplotlib, you can now plot the graph. The good thing about Python is that it comes with these micros and macrons. Not it comes with it. We have also developed simple codes to prepare these micros and macrons. So you have a graph, which of course they plot in the classroom, but now they can now plot this with what? The computer. And when they plot it, they see a beautiful straight line, which we expect from the experiment. And the beauty of Python is that it comes with LaTeX, which is a markup language. And every main scientific journal, if you want to publish there, you have to use markup language. So this encourage in my class, which I teach in computational physics, I have to include teaching my students the use of LaTeX, the LaTeX. Okay. So this is just one example. So you can see from the beginning of the experiment, in fact, every a student does in the experiment, starting first with this setup. You carry out the experiment, then you go on to plot the graph. You can do it with what? With Python. That is the beauty of it. Then we have something else here. We mimic the Fourier transform, which of course is very important in engineering. Okay, so you have 4 types. You have the Fourier series for periodic function, Fourier integral for a periodic or non-periodic functions. You have the fast Fourier transform for continuous functions. You have the discrete Fourier transform for discrete functions. So we'll give an example. We have done a number of these, but we give an example with a simple thing. Now, what you see here as a black box, that is where student problems is. Because in the Fourier transform, you are going to convert a periodic function to a sinusoidal motion. So you need to know calculus. One difficult thing for college student or university student is calculus. Especially in this case, you need to know the integral of trigonometry. And what you see here is so simplified that the equation, sometimes if you ask a student to solve a simple Fourier series problem, maybe it could take 1 hour at minimum for a very fast student, and for a very simple problem in any case, it will take 1 hour, 2 hours, 3 hours. And sometimes they get, what are all these equations you solve here and here? We say, no, don't worry. What we are asking you to do is, this is an equation which is not sinusoidal. We are asking you to convert it to a sinusoidal motion. That is the Fourier series. So we show it here. So you can see what goes there is not a sinusoidal motion. It could be anything. Like I showed in the previous slide, it could be a square waveform, it could be a sawtooth waveform, it could be a triangular waveform, but the output is always what? Sinusoidal motion. So you can see it here. As it goes on, what is coming out is a sinusoidal motion. And when students see this, they say, wow. Then we say, look, all the calculations we are asking you to do is nothing more but change this thing to what? A sinusoidal motion. And I think they do appreciate it, the simplicity. There is something which I have not shown here, but okay, these are more examples of this. But there is something I have not shown here, which of course you can also find in my talk at the US PyCon 2012. It's on YouTube. If you Google my name, you can get it. Then you can also find it at the website. My website. It's on YouTube. It's on the PyCon 2012 website also. There, I gave a talk and it's also recorded, so you can see the video. And that has to do with the Schrödinger equation. Now, yesterday, Alice was talking about the limitation of physics, how classical physics said, oh, there's a problem. The Newtonian physics failed, and it gave birth to what? Quantum physics. The failure of the Newtonian physics, in the real sense, for us physicists, is it's not a failure. It's just that at the level where quantum physics operates is different from what classical physics operates in. Classical physics is for large bodies. I will use terms that are very easy for us to understand. Things you can see. But quantum mechanics operates at a microscopic level. That is, things that are of the size of the atom or subatomic size. So both of them, they are good theories. But as you get smaller, classical physics gives way to quantum physics. And if she were here, I don't know, Alice is here, okay, I would have told her that, look, there's also, that is not the end of the story. We are now having what we call hadronic physics, and that is where I'm working on. Of course, these things takes time to be accepted by the world. We are saying that if you have two particles that are close enough, and you have their wave function overlapping, such that the distance between their nucleus is 1 Fermi meters, then quantum mechanics, like classical mechanics at the other level, becomes invalid. And what you have then is what we call hadronic mechanics. And this is what I'm using to explain my own kind of physics of superconductivity. But of course, it will take some time to be accepted. But that is the reality. We are going to move one day from quantum mechanics. It doesn't mean quantum mechanics has failed. But at this level now, it is no longer valid. And that is hadronic mechanics. All right. So having said that, in quantum mechanics, the greatest thing is that is the Schrödinger equation. Now, one of the things you discover about quantum mechanics is that it says, we often say that it does not appeal to common sense. I am seeing all of you now, but if a quantum particle is here, you are not sure, you won't be able to see it. So one of the things we've also discovered is that a quantum particle can tunnel, that is, if a barrier, that is, if you see the video, you'll see it there. For a barrier, a classical particle, if I throw this stuff now, it will hit it and come back, and that is what we call reflection. But for a quantum particle, if the energy is high enough, there's a possibility that it will tunnel too. And there's also another thing again which is strange in quantum mechanics, and that is the fact that all of you can behave like light. Yes, light can undergo reflection, refraction, diffraction, and interference. And it means all of you being quantum particle, and that is the concept of wave-particle duality, that we cannot behave like light, which is a wave. And by implication, if we shut all these doors here, and we subject you to the right condition, it means you can also escape from this room without the doors. And imagine a student coming from the classical physics, and imagine somebody like me leaving this hall without the door. Then I'm a magician, right? But we say this is not magic, this is what? Physics. And they cannot picture it. So one of the simulations we have done, it will simulate the Schrödinger equation. And when you see it, you see the wave function. When the energy is very far for a wall like this, when the energy is very far, it hits it, and you see the wave reflected, the whole wave reflected. Then when the energy is close to the potential barrier, we are not going to see the same wave. It gets here, part of it will be transmitted across the barrier, while part of it will be reflected. And students are seeing this live. And when you change the energy of the potential such that the potential is now lower than the energy of the particle, then you see the whole waveform transmitted across the barrier. So with that, the student has a clear picture. This, of course, is something that students ordinarily will not have a picture. They will keep imagining. And if you teach quantum mechanics, just maybe you are the best professor in the world, yet if you are teaching quantum mechanics, your student will still squeeze their faces. That is the truth. They will still squeeze their face because they cannot just picture some of these things. But with our simulation, you see the wave function undergoing various behavior as you change the energy of the particle compared to the potential. Okay, so let me quickly rush through a few things. The problems is, okay, here in South Africa, I think light is relatively constant, but it's not like that in some countries. So one problem we are facing with the pack set, how to spread it to other African countries, lack of constant power supplies. Then, of course, there's lack of funding. Then another thing is, I said most of the curriculum, they are compact because of the traditional courses which must be covered by the student. So how do we accommodate computational physics? In my university, some 3 or 4 years ago, we only have it as a first semester course. But after a push, we now have it as a 2-semester course in final year. First semester and second semester. And that is because I'm into computational physics in my university. Okay, then what is the prospect? One of the prospects is, okay, reduction in the in the prices of laptop so that people can get affordable laptops. Not everybody, for the developers, they may not understand, but those of us in the university, we know how it is often difficult for students to get laptops. Then what I do in my university is that if you are in 300 level, in fact, I make it a point that, look, before you move to 400 level, there's computational physics, and you must get a laptop. Then I open a letter. If you feel you cannot tell your parents to get you one, I will do the write-up. My universities are aware of it. Yes, because if you don't do it, you score 0 in that course. It's very clear. So after the first year, there was problem. Second year, we bad, but I think now I'm having a good time because all the students, they come to my class with their own laptops. Okay. Now, we also talk about free and open source Python. Then, okay, it's wide range of applicability, thereby making Python programmers very marketable. Then one of the things is that the ease and flexibility to use the pack, which I demonstrated. These programs, they are very easy, and you can set them up. And you can vary the length easily. They are just small code. You just change the length or change the bulb, and you see everything you want to see. So these are the prospects where, okay, this is something designed by my student, a laptop charger. I know here you have companies that produce laptop chargers, okay, maybe between 300 and 500 rands, but this one comes lesser because it's designed by the student. So it's part of the pack set project. Okay, thank you. Maybe I will carry my luck further, that I will start teaching computational physics right when the child is in the womb. That is just what I want to show. Thank you.
Thank you. Does anyone have any questions for Godfrey?
Thank you. First of all, I would like to say I think I'm quite impressed with the work that you guys are doing. And I would like to find out, you say you have a PackSet PACs.
Yeah.
This is like a tool or collection of programs.
Yes.
So they are freely available or...
Yes, but now we have not put them on the internet.
Also, is this just a Nigerian project, or because it says African, and also which countries are involved?
Yes. The plan is to reach other Africa countries, basically. At the International Center, that is International Seminar on Theoretical Physics and National Development, we have Africa countries coming in. For now, we are able to take care of the few countries within West Africa. Funding is really a problem. Okay, funding is really a problem. Most people who are coming from within Africa, especially students, they require funding. And that fund is not usually available. You know, it's one of the serious problems. If funds were available, then we'll have more students or even their teachers. Because one of the things about the mandate of the National Mathematical Center is a place where you teach the teachers. The teachers in the universities, when they come, because the idea is that you cannot have all the experts in Africa countries in a particular country. You take my university, for instance. I'm a theoretical physicist, also working on computational physics. And if you go around, there are very few people like me within my country. Other areas, they are like that. So the government said, okay, let's have a National Mathematical Center where you now bring these experts from time to time to teach the other teachers, you know, from universities where you don't have this expert. So it is our goal that we'll be able to have other African countries coming to the National Mathematical Center so that we can spread the PackSet project.
Okay, just to finish off, so I want to understand your model. Let's say now there are some African countries that would like to join you guys.
Yeah.
The right channels, are there like ways to collaborate with you in any way?
Very easy.
And also, have you tried the route of, you know, like marrying computer science with physics and then sort of doing double majors where physicists in your university would then learn some computing skills from the computer science department? And
I work with the computer science department. Okay. I told you I'm a theoretical physicist, of course, like Isaac Newton. He's a theoretical physicist, but you also know him as a mathematical physicist. And with my PhD degree, I can work in the mathematics department. I can teach math method. I can teach other topics. So I can work. So in my university, I work with the computer scientists there. Okay. Yeah.
And lastly, as software developers, if you want to help, say, volunteer writing some code, how does one go about doing that for your course, that is?
Okay. Yes, I think the major thing here is if you want to write a program, the first thing you have to understand the physics. So for those developers, the little bit, like I'll give a simple pendulum now. You have to know that the length, when you vary it, it affects the periodic time. If you don't know that, if you don't have any basic idea, then it's going to be a problem. So for any developer who is interested, the first thing is that maybe we want to know the level of his understanding of the problem. So whatever problem we give to such developer, we first make sure he understood the problem first. So when they come, we'll answer them. We can discuss that.
Great. Another question?
I have a rather naive philosophical question. First of all, I'd like to Thank you for a very fantastically interesting talk.
Thank
but
you.
I was wondering, in terms of the discontinuity of Newtonian classical physics and quantum mechanics, it seems to me that when you presented your model of teaching and computational thinking, computational approaches, that computational model seems to be able to cut through that level of discontinuity. And I was wondering, in terms of computational thinking, if you could talk a little bit about how you see it as, is it an extension of the scientific method so that it's instrumental reasoning that operates at a very, minute degree of discrete units so that we can, study the very, very small with it. But the fact that it seems to work and operate still at the classical Newtonian level of reality, does that say something about our ability to sort of reach a mathematical conception of how the world actually really works? In other words, it cuts through both the Newtonian and the quantum and whatever it is that you're seeing as beyond, something like that.
In truth of the matter is that I didn't use that is moving beyond quantum mechanics. It's not a computational thing. It's not a computational thing. It is based there. Let me give you the basic thinking. The basic thinking, of course, is there's a school of thought. Of course, physicists, they think a lot. That believes that, the hydrogen is the simplest element because it has one proton and one neutron. Now, there's a school of thought that believes that the hydrogen that is the proton and the neutron can combine, okay, to form what we call the positron. Okay? And when you have the positron, then it's a different kind of thing entirely. So this is where we are, this is the angle we are looking at the problem from. So we've developed all kinds of, because in physics, what you do is that if you have a brilliant idea, it doesn't matter until you come out with a number. So you have to develop a mathematical method to solve the problem and come out with a number. It is that number that experimentalists we now try to see if they can get or get close to. If they do, then, of course, that means your theory is okay. Otherwise, it has to be discarded. So in hydronic mechanics, if you Google it, you'll see it. Somebody like Professor Sartini has been working on it. Okay? But as usual, the world may not accept everything. Like even this Schrödinger theory we talk about, the quantum mechanics you talk about now, if you read the history, you see those who proposed it. It was not a quiet thing. Schrödinger was one of them. Then Heisenberg was another one. Sometimes the words they say to themselves at conferences are very terrible. Yes. Sometimes Heisenberg will say, why is Schrödinger, this is a Nobel Neuron. But he will say, look, why are you reasoning like a college student? Like when even the wave-particle duality we talk about now, when the man who proposed it, de Broglie, when he proposed it, it was not accepted. Even Einstein did not accept it because the PhD thesis was taken to him, but he says, okay, that there's something in it. Give the young man the PhD. Then, luckily for him, two guys in America were able to diffract. Diffraction is a property of a wave. Light can be diffracted. Then two guys in America, and later the son of J.J. Thomson, they were able to diffract the electron. And electron is a particle. Now they diffracted. So they saw that the electron was now behaving like what? A wave. And that was how de Broglie also got the Nobel Prize. But it was not accepted. So what we are suggesting now may not be acceptable to the world. But if you go to the website of Sartini, he has done so much papers, okay? And he has also come out with even applications of his hydronic mechanics, and they are there.
Do you think computational thinking will be sufficient as a method to...
No.
So it'll be a
I see, of course, computational technique is more or less like a mathematical tool. It's not a physics reasoning. You have to get your physics reasoning very well. Then the next thing is, okay, how do you get a result which can be tested? So this is where the computational thing, if you can solve it analytically, purely mathematically, fine. But where you have limitation, this small head cannot go further than some limit. So you now apply computational technique. So the physics must be clear first. So it's not the computational that gives the result, but rather it is your thinking.
Great.
Okay, thank you very much.
Now let's thank the speaker. Thank you.